Good morning everyone. Today I am going to take named reactions like Clemmensen reduction reaction and also Wolff-Kishner reduction reaction. Clemmensen reduction reaction, that is simply conversion of ketones into alkanes. RCOCH3 is converted into RCH2CH3. Clemmensen reduction reaction. So, in this reaction was first reported by Clemmensen of Park Davis in 1913. Clemmensen of Park Davis, he is the Russian scientist. It is the reduction of carbonyl groups in aldehyde and ketone to methylene group. That means RCOCH3 is converted to RCH2CH3. CH2 is called methylene. CO is converting CH2. This reaction done with zinc amalgam and hydrochloric acid, and it is generally known as Clemmensen reduction. See here mainly we can remember that zinc amalgam, ZnHg amalgam. When the mercury molecule is there, we can say amalgam, zinc amalgam and hydrochloric acid. So this reduction reaction takes place in hydrochloric acid, acidic condition. Clemmensen reduction takes place in acidic condition, whereas Wolff-Kishner reaction takes place in basic condition. Okay. So the general reaction of Clemmensen reaction is ketones RCOR2 can be converted to RCH2R2 in presence of zinc amalgam and hydrochloric acid. Hydrochloric acid means what? It's a acidic condition. In the acidic condition, ketone can be converted to alkane. This type of reaction is called the Clemmensen reduction reaction. Why we are saying reduction means here loss of oxygen and addition of hydrogens is called the reduction. So this is the Clemmensen reduction reaction. So here R1 and R2 is any alkyl groups or any aryl groups, any simple hydrogen groups also we can use. So the mechanism mainly known in this is zinc. It is highly rich of electrons. Actually our ketone O is always a highly electronegative atom. So this is a highly electronegative atom. It always want to take electron from the carbon. So, but here zinc is giving electrons to oxygen. Now, from this double bond, this carbon is getting electron here. This is the specific case. Generally, always carbocation takes place, but because of presence of this zinc, it is highly rich of electrons. It can donate electrons to oxygen. So that's why carbon is getting electron. That is, maybe sometimes we can use negative charge also. So the negative charge is denoted here. This negative charge is coming to here oxygen, and here oxygen is getting the negative charge. That is this triangle form of bond formation takes place. Zinc, oxygen, and again zinc is bonding with the carbon. So that's why this triangle bond formation takes place. This is the intermediate formation. So in presence of zinc and HCl, here from the HCl, what happened? This double bond can donate to electrons to H, and Cl is attached to zinc. The hydrogen is attacking on this carbon, and the Cl is attacking on the zinc, and formation of zinc chloride. At last we need this carbon is getting hydrogens. Actually we need 2 hydrogens here and removal of this zinc chloride. So the next reaction is loss of this zinc chloride and again addition of another hydrogen. We are getting the CH2 methylene bond. Conversion of carbonyl group to methylene bond. This reaction is called the Clemmensen reduction reaction. So zinc is highly rich of electrons. It is donating electrons to oxygen. Oxygen giving electrons to carbon. Carbon is getting negative charge, and here is having rich of electrons. Again formation of the triangle bond. Oxygen is getting the negative charge. So from this hydrochloride, zinc is taking electrons from chlorine and formation of zinc chloride, and hydrogen is attacking on the carbon and hydrogen bond formation takes place. And the next hydrogen is come from another HCl, that is act on carbon, and this formation of CH2 takes place. This is the actual mechanism involved in the Clemmensen reduction reaction in presence of acid, zinc amalgam and acid. This reaction takes place. Whereas in the Wolff-Kishner reaction, in the KOH basic condition, this reaction takes place. We can see in later slides. These are the applications of Clemmensen reduction reaction. This reaction has widely used to convert a carbonyl group into a methylene group. Also important application in the preparation of polycyclic aromatics and aromatics containing unbranched side hydrocarbon chains. That means simply polycyclic aromatics like naphthalene, anthracene, this type of compounds can be prepared by using this Clemmensen reduction reaction. To reduce aliphatic and mixed aliphatic aromatic carbonyl compounds, we can also use this Clemmensen reduction reaction. So here this is a simple aldehyde. Heptanol is aldehyde also containing carbonyl group. This carbonyl group is converted to CH3 group. Heptanol aldehyde is converted to heptane. And here benzyl cyclopropane, that is it is a ketone. CO is converted to CH2, that is allyl benzene formation. We can use this Clemmensen reduction reaction. So now coming to Wolff-Kishner reaction. So this is also same conversion of the carbonyl compounds into the alkane forms. That carbonyl group is again converted to CH2 group, but in the basic condition. See here. The Wolff-Kishner reaction was discovered independently by N. Kishner in 1911 and L. Wolff in 1912. The Wolff-Kishner reaction is a reaction used in organic chemistry to convert carbonyl functionalities into methylene groups. That means carbonyl group can be converted to methylene group. Methylene means CH2. The Wolff-Kishner reaction is an organic reaction used to convert an aldehyde or ketone to an alkane using hydrazine base and thermal conditions. So this reaction requires specific conditions. High temperature is required, base is required, and in presence of hydrazine this reaction takes place. Because the Wolff-Kishner reaction requires highly basic conditions, it is unsuitable for the base sensitive substrates. So this is useful for the acid sensitive substances. In Clemmensen reduction, it can take place the acidic condition. If the compounds are acidic sensitive, we can use the here Wolff-Kishner reduction requirements. So this is the general reaction. So carbonyl compound in presence of hydrazine hydrate in base KOH, and we can use the solvents like glycols, diethylene glycols we are also used here. And here carbonyl groups simply attacks with the NH2 by Schiff's reaction, that is by nucleophilic addition reaction. They can simply loss of H2 and O, water molecule, and this is called the Schiff's base formation, and it's a Schiff's reaction. Actually this is a simple mechanism in the first step only, that is C double bond N and H2 formation takes place simply by the loss of water molecule, and after heat there is the loss of nitrogen gas takes place and formation of the alkane molecule. So here the actual mechanism is involved, Wolff-Kishner mechanism is involved. There is a loss of nitrogen group takes place, nitrogen as a gas, and formation of the simple alkane. So this is the simple general reactions of the Wolff-Kishner reaction, conversion of carbonyl compounds into alkanes in presence of the base and hydrazine hydrate. So the mechanism involved is, see here, our ketone or C double bond O R2. Always oxygen is highly electronegative. It takes electron from the carbon. It always gets a negative charge here, and here is getting the positive charge. And generally nitrogen is having rich of electrons. NH2 is there. Nitrogen is having rich of electrons. It can donate electrons to the carbon. So that's why N is giving electrons to the carbon and nitrogen is getting the positive charge, and there is a formation of the bond takes place. Next, this reaction takes place in presence of base KOH. It can readily give the OH minus ions KOH. That's why here base is required. OH minus is required. This OH minus readily takes the proton from this intermediate molecule. Simply this is the hydrogen of the ketone. So here OH takes hydrogen and formation of a water molecule, and then in presence of water, that water molecule gives one of the hydrogen to the oxygen to get a OH. There is a loss of H and simply NH and NH2 formation, and here highly electronegative oxygen is there. That's why it can takes hydrogen from the water molecule, or any, if we can use any glycols, diethylene glycols, it can donate the protons. So it can takes, and there is the formation of OH bond. Then again OH minus, which is present in the reaction, that is base, in presence of base, that OH minus takes proton, another proton from the hydrogen hydrate, and here is the electrons are there. These electrons are given to the carbon and formation of the double bond, that is R1 C double bond N NH2 R2, and here removal of this OH group takes place as a water molecule. Simply there is a formation of the imine, diimine formation takes place. Diimidine we can say, this formation takes place, and again in presence of base OH minus are there, and again it can takes another hydrogen and loss of water molecule simply, and this N is having negative charge because hydrogen is giving electrons to nitrogen and it is removed as a water molecule, and hydrogen is getting negative charge. So now, and again the OH takes another hydrogen from this nitrogen and loss of water molecule takes place, and next there is a loss of nitrogen also takes place in the form of the gas, like here forming loss of water molecule and N double bond N minus formation, and there is a loss of nitrogen gas takes place, and simply there is a formation of the Rc minus R2H. So now here we need another hydrogen. That hydrogen is given by the water molecule, and that hydrogen is attacked on the this electronegative carbon, and there is the formation of the RCH2R2, that is the methylene. So totally this reaction requires base OH minus, number of OH minus are coming from the base, that is a KOH. That OH always taking these hydrogens, two hydrogens of this nitrogen and these two hydrogens of this nitrogen in every step, and after that at the end there is a loss of nitrogen gas, and simply and removal of this oxygen by the H2O molecule, and next attach of two hydrogens to this carbon and formation of the alkane RCH2R2, conversion of carbonyl compound into the CH2 group. In every step OH is taking hydrogen, every hydrogen is taken from OH. This is the actual mechanism. So applications of this Wolff-Kishner reaction. This reaction has a very broad application in organic synthesis, especially for the multi-valve carbon nanotubes. Carbon nanotubes means there is having number of alkane chains. That number of alkane chains are easily prepared by this reaction. In 2011, Pettus and Green reduced a tricyclic carbonyl compound. Tricyclic, 3 rings containing carbonyl compound using the Hahn-Minlon modification of the Wolff-Kishner reduction. Several attempts towards the decarbonization of tricyclic allylic state containing ketone failed, and the estate functionality had to be removed to allow successful Wolff-Kishner reduction. Finally, the allylic alcohol was installed via oxyplumbation. So finally what it can say is, it is for the synthesis of the multi number of carbon containing compounds we can use this Wolff-Kishner reaction. The Wolff-Kishner reduction has also been used to kilogram scales for the synthesis of a functionalized imidazole substrates. Imidazoles are also prepared by using this Wolff-Kishner reduction. Thank you.